Okay, good morning everyone. Welcome to your week 5 maths lecture for dynamics. The next topic you're going to be learning about within your main lectures is vibration. And basically you'll cover 2 weeks of vibration. You'll learn about free vibration, which is vibration without an external forcing function. And then you'll learn about force vibration, where there is an external forcing function. The aim of these lectures is essentially to show you where all of your vibration equations come from. So in your main lecture, you'll see an equation for undamped, underdamped, overdamped, critically damped vibration. And today we're going to investigate where do those equations come from? How do we know we can use those equations for vibration problems? So firstly, I'll reiterate the definition of free vibration. Free vibration is vibration that has no external forcing function. So essentially, we have some sort of initial condition for the vibration problem. For example, we stretch it, and then we release it. And once we've released it, there's no external force acting on the object. All right? But it is moving, right? It has some sort of oscillatory motion. Now, the first important step for analysing a vibration problem is to draw a clear free body diagram of the problem. Now, springs are common elements we're going to see in vibration problems. A spring applies a force with a magnitude of kx in the opposite direction to x. And a damper is another common element you'll see in vibration problems. So a damper provides a force with a magnitude of c times velocity in the opposite direction to velocity of the object. So you can see the kx and cx dot terms pointing to the left because we're told x points to the right. It's important to also remember there are forces acting in the y direction in this problem. There's a weight force acting down and then a normal force acting up. So that's our free body diagram. Now, once we've drawn a free body diagram, we can apply Newton's second law. Sum of forces equals mass times acceleration. Or in this case, we want to call it sum of forces equals mx double dot, because we're eventually going to form an ODE. So sum of forces in the x equals mx double dot. We had cx dot and kx pointing in the negative directions as our sum of forces from our free body diagram in the x direction. Then moving all the x terms to the same side of the equation, you'll see we have a second order ODE, right? mx double dot plus cx dot plus kx equals 0. If we convert that to standard form, which means the coefficient of this highest order derivative is 1, I have x double dot plus c on m x dot plus k on m x equals 0. Second order differential equation. So you'll see from this, for any unforced vibration problem, we're ending up with a constant coefficient second order ODE, that's homogeneous, meaning the right-hand side is 0. You'll see in the final equation I've inserted some asterisks. They just represent equivalent values for mass, equivalent values for spring constant, equivalent values for our damping coefficient, in any problems where there are multiple masses or multiple springs or multiple dampers. So there are rules we can use to calculate these equivalent values, but my personal preference and what I'd suggest to you guys is just draw the free body diagram, get the equation of motion, all right, and then you've got your equivalent values sorted already. It's a much more reliable method to apply than try to use equivalence laws. Now, when we go ahead and try to solve these vibration problems, instead of describing them in terms of M, C, and K, we typically prefer to describe the problems in terms of natural frequency and damping ratio, where we define the natural frequency as the square root of K on M, and the damping ratio as C divided by 2M omega N. When we modify the equation, so that's described in terms of damping ratio and natural frequency, instead of M, C, and K, we get the following second order ODE, this one here. Now, there are a couple of reasons why we prefer to solve with these two terms. One, it makes the solutions themselves look a lot cleaner. There's a lot less terms in the answers. And two, this damping ratio in particular, we can use to determine what type of vibration is going to occur. If the damping ratio is 0, it's undamped vibration. There's no damping at all. If the damping ratio is between 0 and 1, we get underdamped vibration. If it equals 1, we get critically damped. If it's greater than 1, we get overdamped. So we've got this really fast way of identifying or classifying the type of vibration that occurs if we can solve this damping ratio. So once we've got the second order ODE, how do we propose to solve it? Well, if you recall back to last year, MZB126, when you would have solved second order ODEs, if we're solving a homogeneous, constant coefficient linear ODE, we know the answer is going to be some sort of exponential function. So we assume the solution to the problem is a constant times e to the RT, where we don't know that coefficient, we don't know the power, R. We substitute that into the ODE, which ends up giving us a characteristic equation, with that characteristic equation just being a polynomial equivalent of the ODE. So all our second order derivatives turn into R squareds, all our first order derivatives turn into R's, and all our zeroth order derivatives turn into R to the zeros, so they turn into 1s. Okay? And this characteristic equation we can use to characterize, well, what R is, right? What kind of roots we get. Obviously, in this case, because it's a quadratic function, there are two values for R we'll get when we solve this characteristic equation, right? Now, the type of solution we get for R will affect the form in which we describe the solution to the ODE. If our R values are real and distinct, then the solution is just C1 e to the R1t plus C2 e to the R2t. If our R values are real and repeated, so you get the same number twice, you get your exponential function plus an exponential function times t. And then if you get complex conjugate roots, you get an exponential function times a cos function plus a sine function. All right, and we get that by applying Euler's identity. Euler's identity tells us that e to the power of an imaginary number turns into these trig functions, this cos plus I sine function. Okay, so that's how we're getting these trig functions in that solution, even though we assume the answer was exponential. All right, e to a complex number turns into an exponential times a trig function. Now, mathematically, this top form is the easier form to work with. But the preferred final solution form in this unit will be the second form here. Instead of having a cos and a sine component being added together, it's preferred for you guys in this unit to describe the final answer in terms of a single sine function with an amplitude and a phase shift. And we can convert from this first form to the second form fairly easily with some trigonometry. The amplitude is just square root of c1 squared plus c2 squared. And the phase shift is just the arctan of c1 on c2. We're just forming a right angle triangle because cos and sine are perpendicular. They're orthogonal. Now the reason why this second form is typically preferred for your final answers is because it's much easier to visualize what that solution looks like compared to the cos and sine components. All right? You should be able to sketch what a sine function looks like if you know its amplitude, its frequency, and its phase shift. Right? If you're asked to add two trig functions together, it's a lot harder to sketch what that might look like. I apologize, I've got a bit of a cough today, so sorry my voice is shitty. So that's a brief summary of how we would plan to solve a free vibration problem mathematically. So now what we want to do is we want to apply some mathematics to give us an equation for undamped vibration, an equation for underdamped vibration, critically damped vibration, and overdamped vibration. All right? And if we do this for any value of natural frequency, any value of damping ratio, right, then within this unit you can use those final functions we solve instead of having to solve the entire ODE each time. So recall from the slides, the equation of motion we get for our free vibration problems can be described as x double dot plus 2 zeta omega n x dot plus omega n squared x equals 0. That's the ODE we're trying to solve. And the first step we apply whenever we're trying to solve a constant coefficient linear ODE is we write down the characteristic equation for that ODE. So the long process required to do that is you assume the solution's exponential, you substitute that exponential function and its derivatives into the ODE and factorize. The short way is just to convert the ODE into a polynomial. So anytime we have a second order derivative, I'll put an r squared. Anytime I have a first order derivative, I'll put an r. Anytime I have a zeroth order derivative, just an x, I'll put a 1. So omega squared times 1. See, the characteristic equation is just a polynomial equivalent of the ODE. And then once we've got this polynomial, this characteristic equation, we want to get the roots of it, right? So we can use the quadratic formula to get our roots. These are the roots to our characteristic equation. Now we'll see if we can simplify these roots a little bit. What do we get here? We've got a common factor of omega n squared in these terms. And then a common factor of 4. So we get something like that. The square root of 4 omega n squared becomes 2 omega n. And dividing everything through by 2, right? We can get rid of that denominator. So this is what our roots look like for any value of natural frequency, for any value of damping ratio we may have for a vibration problem. You'll see this solution form looks a lot nicer than what it would if we described it in terms of MC and K instead, since we wouldn't be able to simplify that quadratic formula down with those parameters. So now that we've got the general form for the roots, I want to try and see what our solution looks like for our 4 different types of damping. So the first type of damping we can have is undamped vibration. For undamped vibration, the damping ratio equals 0. So if we see what happens to our roots, given that the damping ratio is 0, the real component of the roots, this bit here on the left is 0, and this bit on the right just becomes omega n times the square root of negative 1. Obviously, the square root of negative 1 is I. So the roots are plus minus omega ni in the case of undamped vibration. Now you should note the type of roots we got here. We got complex conjugate roots. So the solution for our complex conjugate roots, right, is our exponential function times a sine function plus a cosine function. All right? That's the solution we write down whenever we have a case of complex conjugate roots. Now in this case, the real component of the root is 0. A equals 0, right? And e to the 0 is 1, so there's no exponential component to this solution. And then b is the imaginary component. B is our natural frequency. So that's what our solution looks like. Or alternatively, instead of having a sine and a cosine component added together, we can have a single sine function that has a phase shift. Again, that second example is the form we prefer to use, but the first form can sometimes be mathematically easier to use if we're trying to solve if we're applying initial conditions, for example. So undamped vibration has a constant amplitude. Amplitude stays the same forever. It makes sense if it's undamped, right? So let's next look at the second case. So we have underdamped vibration. So underdamped vibration occurs when our damping ratio is somewhere between 0 and 1. So recall that our roots to our characteristic equation look like this. Now to see what type of roots we get, I want to see what sign I get within that square root. Do I get a positive number or a negative number? Well, if zeta is between 0 and 1, I'm always going to get the square root of a negative number. Right? So this tells me I'm going to get complex conjugate roots in the case of an underdamped problem. So if I have the square root of a negative number, it's equal to the square root of positive value times I, times the square root of negative 1. Right? So see how I've flipped the direction around from zeta squared minus 1 to 1 minus zeta squared, and I've put an I at the end. That's what the solution is going to look like for our underdamped vibration problems, no matter what zeta is, so long as it's underdamped. So remember what the general form looks like when we have complex conjugate roots. We have this exponential function times a cos function plus a sine function, where a is the real component, so a is this negative zeta omega n, and b is the imaginary component, which is this function here. Now we give this function here a special name. We call this omega d. All right? It's like the damped natural frequency. Okay? And any problems where, any underdamped problems where there's obviously damping. Instead of oscillating at the natural frequency, you're oscillating at this damped natural frequency, which is slightly different to the natural frequency depending on what zeta is. So what we get is our solution for x. We get e to the power of the real component of our solution. So e to the power of that times t. Times c1 cos the imaginary component, which is omega d, plus c2 sine omega dt. And once again, whenever you have a cos plus a sine component of the same frequency, you can convert that into a single sine function with an amplitude and a phase shift. Like so. So that's what our solution looks like for any underdamped vibration problem. Now the third type of vibration we can get is called critically damped vibration. Which is when the damping ratio equals 1. So once again, we'll refer to the roots of our characteristic equation. Those were the roots to our characteristic equation for any value of damping ratio at all. Now, if we look at what happens given the damping ratio equals 1, so it's a critically damped case. All right, what do we get? We get omega n. And then if the damping ratio is 1, we get 1 minus 1. This is a 0, right? So the roots are omega n, sorry, negative omega n, plus minus 0. So what type of roots do we have here? We have real and repeated. Right? Since we've added and subtracted 0, we get the same root twice. So whenever we get real and repeated roots, x is equal to c1 e to the rt plus c2t e to the rt, where r is our root we got. So in this case, our root is just negative omega n. Sorry, negative omega n. So that's what we get in the case of critically damped vibration. And then the final type of damping we can get is overdamped vibration. which is when the damping ratio is greater than 1. So once again, we want to look at the roots to our characteristic equation and what they would look like in any case the damping ratio is more than 1. So our characteristic equation roots are negative zeta omega n plus minus omega n times the square root of zeta squared minus 1. All right, and then let's think about what happens whenever zeta is greater than 1. Well, if zeta is greater than 1, then this number in here is always going to be positive. Right? So because we're always taking the square root of a positive number for our overdamped problems, we're always getting real roots. All right? So that's what the roots look like. They're real, and they're distinct. Distinct roots. So in any scenario where we get real and distinct roots, then the solution is just C1 e to the R1t plus C2 e to the R2t. All right? Where R1 and R2 are our roots. Remember what this here is equal to? We can say this is equal to omega d. So I can say this is C1 e to the negative zeta omega n minus omega d plus C2 e to the negative zeta omega n plus omega d. Okay? So that's one way you could describe it if you want to describe it in terms of omega d. Or there's another way you can describe it if you want to. In the roots, because each component has a common factor of omega n, you can simplify it that way instead. And then you can use those as your roots if you want to, right? Yes? Oh yeah, forgot the T's. Yep. Cool, thanks for pointing that out. All right, so with that, you can see how we can evaluate all of the possible types of free vibration we could get as functions of time. So from now on in this unit, instead of having to solve a second-order ODE each time to determine vibration behavior, you can just calculate the natural frequency, calculate the damping ratio, and based off the damping ratio, go, well, it's between 0 and 1, it's underdamped, so I can use this underdamped function of time as my solution. All right? Does that make sense? So you don't have to solve the ODE each time. You can use these functions of time we've derived instead. That said, there's nothing wrong with solving the ODEs. You can do it if you want to. You just now have the option of not having to do that, right? Since we've shown the functions of time for every possible value of damping ratio and omega n. Now, we've looked at deriving these vibration functions as a pure mathematics problem up to this part. We haven't really discussed what those different vibration types mean in terms of behavior. The equations we got, the functions of time, should give away what the behavior looks like, but just in case it hasn't, I've plotted that behavior as well. You can see in the case of your undamped vibration, you just have this constant amplitude, sinusoidal motion. For your underdamped solution, you have an exponentially decaying sinusoidal motion. So the amplitude is decreasing over time. For your critically damped vibration, okay, that's the smallest value for damping such that you don't get any oscillation at all. And then overdamped, again, there's no oscillation in the solution at all, but it decays a lot slower than the critically damped case. Now, so far what we've looked at is getting the general solution to these vibration problems, which means we're getting the solution without having any initial conditions, meaning there are still unknowns in our solutions. We had C1s and C2s as unknowns, or A and phi as an unknown. Now, typically what you want to solve is the specific solution to a vibration problem. And to do this, we'll need two initial conditions, because we're solving a second order ODE, essentially. There are two unknowns in the solution. Now, typically those initial conditions are going to be in the form of an initial position of the mass and an initial velocity of the mass. Note that to apply the initial velocity condition, you'll need to derive your equation for x. So you have an equation for velocity, where you can sub that initial condition in. So now we're going to look at applying initial conditions to a problem. I want to solve the position of an undamped free vibration, given I'm provided an initial value for x, which I've called x naught, and an initial value for velocity, which I've called v naught. So for undamped free vibration, we've already come up with what the general solution looks like. This is what the general solution looked like for our undamped free vibration. In terms of a cos and a sine component, we could have also done it in terms of an amplitude and a phase shift. Now, I want to apply these initial conditions to the problem to try and solve what C1 and C2 are equal to. Now, the first initial condition I can apply straight away because I already have an equation for x. So my first initial condition states that the initial value for x is x naught. And to evaluate x at t equals 0, I want to substitute t equals 0 into my function for x. All right? So what happens when I substitute t equals 0 into these functions? All right, I get a cos of 0, which is 1. And I get sine of 0, which is 0. So I solve that C1 is equal to the initial value for x. All right? C1 is x naught. Now I have a second unknown, C2, which I can solve with my second initial condition. Right? But that initial condition is for velocity, for x dot. So I'll have to derive x with respect to time before I can apply that initial condition. The derivative of cos is negative sine, right? And remember, we want to use the chain rule because we've got a linear function of time within a cos function. So the derivative of the inner function, omega n, comes out the front when I derive. And the derivative of sine is cos. And once again, we want the chain rule, which is why the omega n comes out the front. So that's our equation for velocity. And now we can apply that second initial condition. We know the initial value for velocity is called v naught. And now we want to substitute t equals 0 into that velocity equation. So we know the sine function becomes a 0, subbing t equals 0 in, and the cos function becomes a 1. So C2 equals negative v naught over omega n. Right? So now we have our solution, our specific solution. X of t is x naught cos omega n t plus negative v naught on omega n sine omega n t. Good question. It shouldn't be. It's positive. All right. So solution's x naught cos omega nt plus v naught on omega n sine omega nt. I remember what I said, how in this unit we prefer to describe our answer in terms of an amplitude and a phase shift of a single sine function. So at this point we'll go ahead and we'll convert from this form into a form that only has a single sine function in it. So remember, to get the amplitude of this single sine function, we apply Pythagoras' theorem to the amplitude of the components. So this is what our amplitude looks like, the square root of x naught squared plus v naught on omega n all squared. And then our phase shift is the arctan of C1 on C2. where C1 is x naught, right, and C2 is this V naught on omega n. So that's what the specific solution looks like for an undamped vibration problem, given any initial position, any initial velocity. You can just sub your answers into that equation and you've got your answer. Any questions there at all? Is that making sense to people, how we're applying those initial conditions? Okay. You want the coefficient of the highest order derivative to be 1. Yeah. So that's why when I was deriving that ODE, it initially had an m out the front, and I divided everything by m. Okay? So just to summarize, all right, you can now see where all of your free vibration general solution functions come from. You'll be showing those functions again in the lecture, I believe. So you can use those functions. You don't have to solve the whole ODE. The idea when you're solving these vibration problems yourself is to firstly draw a clear free body diagram of the problem. Secondly, apply Newton's second law, get your equation of motion. This will deal with any equivalent values for K and C in problems with multiple springs, multiple dampers. Thirdly, evaluate the natural frequency and the damping ratio. Okay? And then once you've seen the damping ratio, you know what type of vibration you have, you can write down the general solution to that problem. So you skip all the ODE stuff, you just write down the general solution at that point. And then after that, you apply your initial conditions. All right? In some cases, your lecturer might be nice enough to show you what the specific solution is for any initial conditions, like I did with the last example. But there are going to be some cases, perhaps, where you're not given those equations, so you have to apply the initial conditions yourself. So please make sure you're comfortable with those that initial condition process I applied at the end of the lecture. Other than that, that's it.